in back to 4 dimensions in 4D Euclidean space. And let's just consider a theory that has some fermions and is coupled to electromagnetism. It won't change, I'm going to say it won't change very much if we consider a non-abelian gauge theory, but I'll leave that discussion to tomorrow for the most part. Where our fermionic part of the action will be the most important part for us today. It's just the usual case where we've got a massless fermion. Okay, so we can define an effective action for our gauge field by integrating out our fermions. So here, gamma of A is the effective action for gauge field. It's just defined by doing the path integral over the fermion of the full action, which depends on psi bar and A. So this effective action doesn't depend on the fermions. We've integrated them out. So it should be invariant under chiral transformations. And the invariance of this effective action for A under chiral transformations is going to be the way that we'll see why the chiral symmetry has to be anomalous. So to do that, let's consider a local chiral transformation for which psi goes to psi prime, which is e to the I theta of x, gamma 5, psi. Psi bar transforms the same way. So we know that this action is invariant under global chiral transformations. But now we're making a local chiral transformation, so we'll pick up an extra term. So fermion part, the full action will be invariant under the global part, but we'll pick up a contribution when the derivative acts on theta, which we can integrate by parts to write as integral of theta d mu j5 mu. Okay. So the effective action should be invariant under this local chiral transformation because our gauge field is invariant under that transformation. So that means that we should have that the variation of the effective action with respect to theta of x evaluated at theta equals 0 should vanish. So that just says that the action for the gauge field should be invariant under this chiral transformation. Which, since we know what the e to the minus gamma is, we can write this in terms of a path integral. This is the functional derivative with respect to theta of the integral psi bar psi e to the minus s minus integral d for x theta mu j mu 5 evaluated at theta equals 0. We've just transformed the Chiral transformation on our path integral expression for e to the minus gamma. And so this is a straightforward functional derivative to evaluate. There's only one place that this depends on theta. And we're setting theta to 0, so we evaluate this functional integral, functional derivative, we get e to the minus s, and when we act with the functional derivative, we just bring down one factor of d mu, d mu 5. Now this is just the path integral expression for the expectation value of j mu 5, of the divergence of j mu 5. Which tells us that 0 is equal to the divergence of the axial current, which is not what we expected at all. That's what would happen if the axial current was conserved. So something's going wrong here. Can anyone point out a mistake?
Something else should be varying?
Something else should be varying, yes. True. Any ideas what?
The p?
The measure. Okay. Yeah. So the measure, the error here is in the first line. So this is not correct. The measure is not invariant. So this was first pointed out by Fujikawa, 1979. So in order to derive the anomaly and fix this equation, we need to figure out how the measure transforms under this Chiral transformation. All right, so the measure is not invariant. In fact, it transforms with the inverse Jacobian because it's a fermionic field. So if we do a chiral transformation, we'll get a determinant of exponential of I theta gamma 5 to the minus 1. Sorry. And similarly for psi bar. And we could derive this just by discretizing our measure, like we saw many times in QFT2. I won't go through that, just using the result that we get the inverse Jacobian. Okay. So this means that we were missing a term in our first line up there. And so the correct equation should be that the functional derivative of e to the minus gamma of, with respect to theta of x, evaluated at theta equals 0, should be functional derivative of integral psi bar psi e to the minus s minus theta dot j mu minus, I can just move the determinant of an exponential into the exponent. I'm using the determinant of the exponential as the exponential of the trace. So we get here this expression. And so we've got this new term here that we need to evaluate in order to find the anomaly. So note, I'm using the notation from QFT2. So this means integral e4x of theta of x in j5 of x. And this trace here is both a matrix trace and a functional trace. And I'll say more about that in a minute when we try to evaluate it. So this is the term we want to calculate. That's our goal. And we'll spend the bulk of lecture actually trying to understand this term. So how can we calculate trace of theta gamma 5? So first of all, once we have this, when we take the functional derivative, we'll bring down a new term. So this depends on theta too, so we'll get a new term that will correct our incorrect derivation over there. And so we'll find that the axial current is not conserved, but there's a new term in the equation. So that's why we want to calculate this term. And so in order to calculate this trace, it will be useful to go to an eigenbasis. Of E slash. So E slash phi n is lambda n phi n. So in Euclidean space, this is one of the main reasons we're doing this calculation in Euclidean space, D slash is Hermitian. So it has a complete set of orthonormal eigenfunctions with real eigenvalues. So D slash is Hermitian, and in Euclidean space, what we mean by d mu, it's conventional to basically get rid of all the i's. So we'll define d mu as small d mu plus a mu with no I here, and we'll define the gamma matrices to be anti-Hermitian. So with these definitions, then this is a Hermitian operator. And these are a complete set of eigenfunctions, which means several things. It means that sum phi n of x dagger phi n of y is delta x minus y times the identity in spinor space. And the integral of phi n of x phi m of x is delta nm. So we can expand out our spinors in terms of these eigenfunctions. We can write phi n as a sum of an phi n, and similarly for psi bar. And here, the an and bn bars will be Grassmann variables. So in this basis, we can write out the trace of theta gamma 5. So this trace means both a functional and matrix trace. So in this basis, the functional trace means we sum, we sandwich this between a complete set of orthonormal of our eigenfunctions. So I can write this as phi n dagger alpha of x, theta gamma 5 phi n of x. And it also means a trace over the Dirac indices, which means we should put an index alpha here, alpha beta here, and beta here. So it's both a functional and a matrix trace. Now, we can evaluate this. So it depends on x. We can evaluate this using the completeness of the eigenfunctions. And what we get is just delta x minus x, theta of x, times the trace gamma 5. We've just used basically this identity. Now you may see a problem. So we have here delta of 0, which diverges, and a trace of gamma 5, which is 0. So we have a completely ambiguous answer. So in order to make sense of this, we're going to have to introduce a regulator. And it's worth pointing out that this is a UV divergence. So this divergence comes from a delta in position space at 0. So that when the distance is going to 0, you can also write this. So a delta for 0 in position space is the same as xx. There's the integral d4p of x e dx, which is integral d4p over 2 pi to the fourth e to the ip dot x minus y, evaluated at x equals y. So this is, you can see explicitly here that it's a large momentum divergence. This is UV divergence. Any questions so far? Okay. So in order to make sense of this, we need to introduce a regulator. And one way we can do this is just to insert a function f of k squared, which has the properties that f of 0 is 1, and f and all its derivatives vanish at infinity. For example, we could choose f of k squared to be e to the minus k squared, but precise form won't matter here. So if we do this, we can insert the regulator in the following way. So write our trace of theta gamma 5, limit lambda goes to infinity, integral d4x, sum of theta phi n dagger, gamma 5, f of lambda n squared over lambda squared. So this will reduce back to our earlier expression if we take this limit, lambda goes to infinity, because f of 0 is 1. Just disappears. Okay, so write this in another way. So since phi n is an eigenfunction of d slash, we can rewrite this as f of I want a minus sign here. Yes, minus d slash squared or lambda squared. Yeah. Phi n. We can then Fourier transform. Fourier transform. twice. We'll get phi n tilde dagger of k prime times gamma 5 f minus b slash squared lambda squared phi tilde n of k e to the I k dot x. Yeah. And so k prime. So it would be, if we can bring this, so this is all, this f of d slash is acting on this here. And what we want to do is to bring these e to the I k prime x and e to the I kx together. Then we can, that will let us simplify this expression. And so to do that, we can note that d slash of g of x e to the I k dot x is e to the I k dot x I k slash plus d slash acting on g of x. So we just got two terms from the product rule, and one will react on the exponential, and the other one acting on the g. So using this, rewrite our trace. The limit lambda goes to infinity. Of integrals of sum by n tilde dagger e to the I k dot x the minus I k prime dot x gamma 5 f of minus d slash plus I k squared over lambda squared by tilde of n. Okay. So now we can again use the completeness of the eigenfunctions. So we use this relation, which we can get just by Fourier transforming the position space relation. So this in momentum space just gives us 2 pi to the 4th delta of k minus k prime times the identity in spinor space. Then we get the trace of theta gamma 5 is the limit as lambda goes to infinity integral of over x and k, and we can use, if we use this relation, we will get rid of the phi n dagger and phi n, and get a delta k minus k prime, which we can use to do the k prime integral. And so what we'll be left with, the that will set k equal to k prime, which will cancel off these exponential factors. And so all we'll be left with is the trace of theta gamma 5 f of minus d slash plus k slash squared over lambda squared. Okay, so now we've made some progress. And we can evaluate this by Taylor expanding. So this is the limit. Lambda goes to infinity. Roll d4x, d4k over 2 pi to the fourth. Trace theta gamma 5. Taylor expansion, we get sum n equals 0 to infinity, 1 over n factorial. So we're Taylor expanding around k squared over lambda squared. And then we just get the nth derivative of k squared over lambda squared. Okay. Any questions so far?
So the small trace there is a trace in the matrix.
Right. This small trace is a trace over the Dirac indices.
Yeah.
So here, gamma 5 is a matrix.
Yeah.
But we also have a bunch of gamma matrices in here. So d slash. Small big trace was the trace over the Dirac indices in addition to a functional trace.
Okay. And the theta, why don't we keep it this sign?
It could we can pull this out of the trace.
Okay.
So this is the same as this is equal. We can also write this as theta. So remember, we've been computing for a while. What we're trying to do is trying to compute the extra term in this equation on the top board. So we're trying to find the quantum equation for the divergence of the axial current. So, and the extra term we got, because the measure wasn't invariant, was this trace of theta gamma 5. So, and we've made this much progress in computing it after we've regularized it. And so now, the next thing we can do is evaluate this matrix trace over the Dirac indices. And to do that, we note that gamma 5 is traceless, and the trace of gamma 5, gamma mu, gamma nu is also 0. So the first term that survives is the d slash to the fourth term. So n equals 2, and d slash to the fourth is the first term. And so that gives us the trace beta gamma 5. The limit lambda goes to infinity. Integral d4x, d4k. Theta. Trace of gamma 5. We have a half d slash to the fourth over lambda to the fourth, f double prime k squared over lambda squared. That's our n equals 2 terms, and there'll be higher order terms. We'll start at 1 over lambda to the sixth. And now we can take the limit that lambda goes to infinity. So if lambda goes to infinity, these terms will disappear. Really, the only term we care about is this n equals 2 term with the trace of gamma 5 and 4 gamma matrices. And we can evaluate that term using the identity, which, since we're in Euclidean space, is missing an I. So we get 4 epsilon mu nu rho sigma. In Minkowski space, there'd be an I here. Of the more familiar version. And so using this identity and taking the limit, we get so 1 over 32 pi to the fourth integral of x theta integral d4k over lambda to the fourth for epsilon mu nu rho sigma d mu d nu d rho sigma. And then f double prime k squared over lambda squared. All right. So we're almost done. What's left to do is evaluate the k integral. Which is not terribly difficult because we're in Euclidean space. So what we get, we just look at the momentum integral. So the only thing that depends on k is f. And so we can make a change of variables here and set q to be k squared over lambda squared, and also go to spherical coordinates.
Isn't it the lambda to the fourth?
Thank you. And if we also go to spherical coordinates, what we get is the integral of q dq f double prime of q. times an angular integral. Angular integral just gives us pi squared. That's the surface area of a sphere in four-dimensional Euclidean space. And we can evaluate this integral using integration by parts. So we get pi squared q f prime at 0 and infinity minus the integral dq f prime of q. And now we can remember how we chose our regulator. So we chose our regulator so that f of 0 was 1, and f and all its derivatives vanished at infinity. So that means we can get rid of this first term, because at the lower boundary, q is 0. At the upper boundary, f prime is 0. And so we're just left with this second term, which gives us pi squared times minus f of q, evaluated at 0 and infinity. And again, at infinity, that gives us 0. And at 0, f of 0 is 1. So we just get pi squared for this integral. You can also simplify our result using the identity for epsilon nu rho sigma d mu d nu d rho d sigma is epsilon mu nu rho sigma times the field strength f mu nu f rho sigma. So I'm not going to derive this, but it might, not surprising, f is just related to commutator of the d's. So using this identity and the momentum integral, we have finally figured out what the trace is. So trace is trace of theta gamma 5 is the integral of theta over 32 pi squared epsilon mu nu rho sigma f mu nu f rho sigma. And so this is going to give us a new term in the equation for the divergence of J5. And so what we get is that d mu J5 mu is 1 over 16 pi squared epsilon mu nu rho sigma f mu nu f rho sigma in Minkowski space. So this is our anomalous non-conservation equation.
This is only expectation values or not?
Yes. So this is the we've included quantum corrections. So if we were to restore h bar, there'd be an h bar over here. So classically, it would be conserved, but once we turn on mechanics, then it's not conserved.
No. Yeah, sure. But what I say is that we will put that inside of our path integral.
Yes.
We'll take the functional derivative with respect to theta.
That's right.
We'll get it that the
Expectation value,
of
right.
mu is going to be the expectation value. Okay.
Yeah, in our path integral, we had an expression like this. So, and so this 2, I think I just erased it. But, oh, no, 2. Yeah. Yeah. So going in this last line here, we had a factor of 2i. That's where the 32 went to 16 pi squared. And so in Euclidean space, there would be a plus I. And in Minkowski space gives us a minus I from multiplication. So again, we see that the axial current is not conserved, and its non-conservation is related to the presence of some gauge fields. So as you can guess, not very much in this derivation relied on the fact that at the beginning of lecture, that we're just considering the abelian gauge theory. We're starting with Maxwell theory. So if we were dealing with a non-abelian gauge theory, the only thing that would change, we're talking about the axial current conservation with the abelian axial symmetry, e to the psi goes to e to the I theta gamma 5 psi. The only thing that would change if we considered a more general non-abelian gauge theory is we would have a trace over here. So trace on the right-hand side.
And we're treating F as, well, A as a background field, right?
So that's a so here we've so this is an entirely quantum theory. So we're this was the quantum effective action for the gauge field. So yesterday we treated our gauge field as a background field. That was not strictly necessary. We could have derived the same. Basically, I could have justified the derivation yesterday using the Born-Oppenheimer approximation. So the characteristic oscillation frequency for the fermions, you can show in the Schwinger model, is much higher than the characteristic frequencies for the gauge field. So it's a consistent approximation, just to treat the gauge fields as fixed and solve for the fermion field in a fixed background, and then later include those corrections if we wanted to go to higher order. I justified it in a different way, but it is entirely possible to justify it entirely classically. So quantum mechanically without, I justified it considering yesterday considering the gauge fields classically, but that was not necessary. It treated it quantum mechanically the entire time. Okay, so that's the path integral derivation. In the last few minutes of lecture, I just want to say a few words about another derivation, another way to see where the anomaly comes from, that you'll fill in many of the details in tutorial this afternoon. And in 4 dimensions, the anomalies come from triangle diagrams. So in 4D, one way we can see where the anomaly comes from is by trying to compute the expectation value of J5 so the axial current with 2 copies of the vector current. And we can call this I and 5. And so this expectation value corresponds to a triangle diagram. And so each of the currents involves 2 Fermat fields. And so we could represent this expectation value in terms of Feynman diagrams just by using Wick's theorem and finding all the ways to consistently contract the fermion fields in the currents. So remember, J mu was psi bar gamma mu psi, and J mu alpha 5 was psi bar gamma mu gamma 5 psi. And so we can contract these in 2 different ways, giving us 2 different Feynman diagrams. Where we've got some momentum flowing into each of the vertices. Or we could represent these with truncated legs, but there's no external fields in this expectation value. And so if the axial and vector currents are conserved, then we should have we can track the momentum with this expectation value, we should get 0. So for momentum space, but if we went back to position space, this would just be saying that the divergence would be 0. And you'll show in tutorial that it's impossible to set these all to 0 simultaneously. So we can set some of these to 0, but not all of them to 0 simultaneously. So this is a way to see the anomaly as the conflicting requirements. So next time, we'll talk about non-abelian gauge fields. And so there's no problem with the chiral anomaly we found so far, the abelian anomaly. In fact, it can be used to explain experiments like the decay of the neutral pion. But the anomaly we're going to talk about next time, which also can come from triangle diagrams like this, but for non-abelian gauge fields, can cause serious problems. So we have a non-abelian gauge theory. And these two diagrams are non-zero. This gives us a new one-loop contribution to the 3-gauge boson vertex. But as we saw in QFD2, gauge invariance requires a very special relationship between the coupling of the 3-gauge boson vertex and the 4-gauge boson vertex. The 4-gauge boson basically has to, coupling constant has to be the square of the 3-gauge boson vertex. So these types of diagrams can spoil that relation and ruin the gauge invariance of the theory. So furthermore, if we have these types of diagrams that are non-zero, we can also have diagrams like this. That will give a mass to gauge boson, again spoiling the gauge invariance of the theory. So these can spoil gauge invariance for non-abelian gauge theories. And gauge invariance is necessary for the renormalizability and unitarity of non-abelian gauge theories. So if we lose gauge invariance, then we'll lose renormalizability and unitarity. And so although it's possible to include fermions in non-abelian gauge theories, if we do so, we have to be careful. If we have the wrong type of matter, it lives in the wrong representations, we can develop non-abelian anomalies that will destroy the consistency of the theory. And so that's what we're going to look at tomorrow. We'll see why the story is different for non-abelian gauge theories and how we can consistently include matter, fermions, in non-abelian gauge theories in a way that all the anomalies cancel. Any questions?